Hello students, in the last video we discussed about column space of a matrix. So column space of a matrix means it is the linear combination of all columns of matrix A. Suppose you are taking n columns, then we are taking the linear combination of all columns as a vectors, then we are taking as this B belongs to column A. So see some problems on column A. Find the matrix A such that W belongs to column A. So one vector which is belongs to column A is given. We have to find the matrix A. We know column A is the linear combinations of all columns in A. So we are taking this vector and we are taking A, B as scalars. Then when you are taking common A and B, then you are getting two vectors because how many scalars are given, that much of vectors will come for linear combination. That's why we are taking the vector here a plus b minus 7a. Here b is not given, so 0 into b we can write and take a common, then the vector will be 6 1 minus 7. Similarly b common means this vector, so a into v1 plus b into v2. So this is the linear combination of these two vectors. So linear combination of any two vectors is nothing but what? Columns of matrix A. That's why v1 taken as first column, v2 taken as second column for the given matrix, required matrix. Similarly, we can see one more problem. Here one vector belongs to column A is given. We have to find the matrix A. Here what are the scalars given? R, S, T. So we should get three vectors. So take the vector. R is not given. So 0 into R plus 2 into S plus 1 into T. Similarly, we can write the remaining one. R, S, T is not given here. So 0 T and R, S, T. Now take R common. Then the vector will be 0, 1, 3, 2. Similarly, S common means 2, minus 1, 1, minus 1. T common 1, 2, 0, minus 1. So we are getting here three vectors which is the linear combination of these vectors. Then these vectors are nothing but columns of matrix A. So A equal to V1, V2, V3. This is the required matrix. And similarly here same type of questions. Column A is given and B, C, D are scalars given. So we should get three vectors by taking B as common, C as common, D as common. So we are writing here 1B minus C plus D is not given, 0 into D. Similarly we can write all the numbers, all the columns. Then we can take B as common, C as common, D common, then 0, 3, 3, minus 3, 1. So three vectors will come. So this is the linear combination of these three vectors in the sense A is having the columns as V1, V2, V3. So here is one question. A matrix A with 3 rows and 4 columns, 3 cross 4 matrix is given. If the column space of A, column A is a subspace of R power K, then find the value of K. That means we know that column A is a subspace of obviously R power number of rows. So rows are here 3 and columns are 4. So column A is a subspace of R power. We know that R power number of rows. But what are the rows here? 3. That's why K is 3 here. Similarly, null A is obviously a subspace of R power number of columns that already we discussed in previous videos. So null A is a subspace of R power number of columns are n. N is 4 here. That's why K equal to 4 here. Similarly, we can see one more question. Find the value of K if null A is a subspace of R power K. Null A is always remember null A is subspace of R power number of columns. Column A is subspace of R power number of rows. So K means here we have to choose rows, here we have to choose columns. So in the first question, in these 2 rows are given and 1, 2, 3, 4, 5 columns are given. So m equal to 4, n equal to 2, and we know that null A is a subspace of R power number of columns, that's why columns are 2. So K equal to 2. Similarly, column A is a subspace of R power K, but column A is subspace of R power m, we know that, that's why K equal to m, which is equal to 4. Similarly, see the next question, 1, 2, 3, 4, 1, 2, 3, 4 cross 3 matrix here. So null A is a subspace of R power number of columns, that's why K equal to 3 here. And column A is a subspace of number of rows, that's why K equal to 4 here. Similarly here, 2 rows, 1, 2, 3, 4, 5 columns. So m equal to 2, n equal to 5. Obviously null A is a subspace of R power number of columns, so K equal to, columns are 5 here. And column A is the subspace of number of rows, that's why K equal to 2. See here last one row with 5 columns. So m equal to 1, n equal to 5, and null A is subspace of R power number of columns, so 5. And column A is subspace of number of rows, that's why K equal to 1 here. So see here, null A and column A, we have some contrast between these two So null A is obviously subspace of R power number of columns. Column A is a subspace of R power number of rows. Here are 4 questions for us. One is any vector is given. Check whether that vector belongs to null A or not. Then we need to verify only one condition, Ax equal to 0 bar. If it satisfies this condition, then we can say this x belongs to null A. Whereas any vector is given, is it belongs to column A, that means directly we can't say, we have to take b equal to Ax, and we are taking one augmented matrix. If it is consistent, then we can say that vector belongs to column A. But find any vector in null A or find any vector in column A means we need to find the vector, in the sense directly we can say in column A, because every column in A belongs to column A. Suppose one matrix we are taking, every column belongs to column A. So easily we can do. But find any vector in null A means we need to take augmented matrix and we have to solve and take independent variables. Then only we are getting null A vector. So here are 4 methods. Find any vector in null A, any vector in column A, and check whether the vector belongs to null A or vector belongs to column A or not. Here is one question. Matrix A is given. Find a non-zero vector in column A and non-zero vector in null A. So find non-zero vector in column A. Already we discussed previously that any vector in column A is nothing but any column in matrix A belongs to column A. So here non-zero vector in column A means take first column which belongs to column A, or else you can take second column which belongs to column A, because column A is span of these all vectors, in the sense span of linear combination of all columns in A. That's why we are taking any column in A which belongs to column A. But to find a non-zero vector in null A means we need to take the definition of null A. What is the definition of null A? X is belongs to any vector which belongs to R power number of columns, and Ax equal to 0 bar, then this x belongs to null A. So x belongs to R power number of columns are here 4. That's why R power 4 means we should take the entries as x1, x2, x3, x4 and take the condition Ax equal to 0 bar. Ax equal to 0 bar vector entries we are taking. How many number of rows are given, that much of zeros we should write here. Then only we are getting 3 equations. Or else for simplification we can take augmented matrix A 0 bar, A 0 bar, and how many possibilities are of rows can be zeros, that we should converting into 0. Like this may be converting to 0, this also may be converting to 0. Like that, how many possibilities are there, that much of times we have to take the row operations. So see here, minus R2 minus 2 plus 2 is 0. So R2 implies R2 plus R1. Then R3, how it will be 0? 2 into R3 minus 3 into R2, then it will become 0. So take the first row as it is, R2 plus R1, 0. Right? R2 plus R1, minus 1, 7 minus 2, 5, 3 plus 1, 4, 0 plus 0, 0. Similarly, 2R3 minus 3R1, 2R3 minus 3R1, 0 here, and 2 means 14 minus 3 into R1, 12, that is 2. Similarly, we can do the next one also, minus 8 into 2, minus 16 plus 6 here. So, minus 10. Here also 9 plus 8, that is 12 minus 3, it is 9. So see here, here also we may convert this into 0 by taking second row, that is R3 plus 2 into R2, then it will become 0, right? So take these 2 rows as it is, here 0, 0, here minus 10 plus 2 into means plus 10, this is also 0, and here 9 plus 2 into means 8, 9 plus 8, 17 will come. So possible zeros are completed. Now we can converting into equations like 2x1, 2 into x1 plus 4 into x2 minus 2 into x3 plus x4 equal to 0. Like this we can converting into equation like 0 into x1 minus x2 plus 5x3 plus 4x4 equal to 0. Similarly 17 x4 equal to 0. From this we can get x4 as 0 And from this equation, x2 equal to 5x3, x2 take it this side, then it will be like this, and x4 is 0 here, that's why x2 equal to 5x3. Similarly, we can do 2x1 equal to minus of this all terms, take it into other side, then substitute x4 and x2 in this, then you are getting x1 as minus 9x3. So, what is x? x1, x2, x3, x4. Substitute x1 equal to here 9x3, x2 equal to previously 5x3, and x4 is 0 we got, and x3 is independent variable, that's why we are taking x3 as it is. And now take x3 common, then you are getting one vector which is called a vector which is in null A, which is a non-zero vector. So, to find any non-zero vector of null A, we have to take the augmented matrix A 0 bar and solve and take independent variable as common. Similarly, we have one another problem. A is given, U and V vectors are given. If U is in null A, then could U be in column A? So, we have to check U is in null A or not, and also U is in column A or not. Let us check. If U is in null A means only we need to verify the condition that A into U equal to 0 bar according to the null A definition. So, any vector is belongs to null A means that vector must be belongs to R power n, and also A equal to 0 bar. Obviously, it has 4 entries, right? R power n means 4 here. So, it must contain 4 entries. So, it already contains, so it is belongs to R power 4. Only we need to verify the condition AU equal to 0 bar. So, A into U, first row into first column. 2 3s are 6, 4 minus 8, minus 2 into minus 1 plus 2, 0. And second row into first column. Second row first column. Third row into first column. 3 3s are 9, 14, here plus 8 plus 0. Like this we are getting some vector which is not equal to 0. In the sense AU not equal to 0 means U does not belongs to null A. And could U be in column A? So, column A is obviously subspace of R power m, number of rows, but U contains 4 entries, but rows only 3. So, see here, column A is subspace of R power number of rows, but rows are 3 here. So, it contains 4 entries, that's why it does not belongs to R3. So, no need to verify for column A, simply U does not belongs to column A. Similarly, we can check for V is belongs to column A or not. Yes, we have 3 entries, so it is belongs to R3, and check whether this is belongs to column A or not means we are taking augmented matrix A and V. Here B is given, AB we can write, here V is given, that's why we are taking AV augmented matrix and write matrix A and V here, and do row operations. First do row operations like how many are converting into 0? Let us see. This is R2 plus R1. R2 plus R1. Here same 2R3 minus 3R1. Then R2 plus R1 minus 1 here and 5 here and 2 here. Here this plus this means 2 here. Similarly 2R3, 2 into 3, 6 minus 3R1, 6. 6 minus 6, 0. Similarly 2R3, that is 14 minus 3R1, 12. This is 2. Like this we can do for every number. Then here again R3 minus plus 2R2, then it will be 0, right? That's why R3 plus 2R2. R3 plus 2R2 is 0. R3 plus 2R2 is 0. R3 plus 2 into means 4. 15 plus 4, 9 here. R3 plus 4. 4 minus 3 is here R3 plus 2 means 4 minus 3 is 1 here. Now, suppose when you are converting this as 0, then these will be non-zeros, right? Now, we need to check one condition, that whether the system is consistent or not. When we can say the system is consistent, in the sense, take this matrix A and find the rank of A. Rank of A is nothing but number of non-zero rows in A. How many number of non-zero rows here? 1, 2, this is also non-zero rows because 19 is not equal to 0. So, rank of A is 3 here, and rank of augmented matrix. Rank of augmented matrix means total matrix we can see. How many number of non-zero rows? 1, 2, here also non-zero row 3. So, rank of A equal to rank of augmented matrix, then we can say the system is consistent. In this case, V is belongs to column A. Suppose here we are getting 0, suppose. Then what will happen? Rank is 2 here. and this total is 3. That's why it is inconsistent in the sense it does not belongs to. So what we need to check is, after doing row operations, we need to check the condition that rank of A equal to rank of augmented matrix, right? So here both are equal in the sense V belongs to column A. Similarly, V belongs to null A or not. What is the definition for null A? V must be belongs to R power number of columns, but V contains only 3 entries, so it does not belongs to R power 4, right? So it does not belongs to R power 4 means it is not a subspace of R power 4. So V does not belongs to null space of A. So in the next video, we will discuss about linear transformation and problems.